Hello, everyone. My name is Marius Bogoevici. I'm a software engineer for Pivotal, and I'm the project lead of Spring Cloud Streams, one of the projects that we're going to talk today. I'm going to introduce you today to stream processing in the cloud with data microservices, and basically what this does entail is an overview, and we're actually going to code live some message-driven microservices with Spring Cloud Stream and orchestrate them with Spring Cloud Data Flow. So these are the two main targets for today. In terms of the title and the problem that we are trying to solve, obviously, stream processing is a domain that has been mentioned. It has gained a lot of popularity recently. When you think of it, you typically think of use cases like preventive maintenance, fraud detection, log analysis, QS measurement. Essentially, use cases that have to do with processing flows of events, continuous flows of events. And they're slightly different from, let's say, more traditional event-driven systems in the sense that they're not responding to sporadic individual events. In most cases, they try to monitor the state of an application and extract information about its state and try to react to various changes. That's a very, very typical use case. I mean, that's not to say that there is not an overlap with traditional applications as they start communicating through a more discrete event model. And actually, as we will see with our data microservices, large groups of applications communicating with each other are very similar, like even if they're not necessarily processing data, are very similar to in nature to stream applications. The same patterns apply in both cases. One characteristic of these stream processing applications is demand for high throughput and low latency. What has been usually the domain of batch processing has basically moved more towards the real-time realm. Quantities of data are growing, but the expectation is that the analysis is done, as I said, closer to real time. For example, it was acceptable 50 years ago to detect fraud on your monthly, a fraudulent transaction on your monthly statement. However, right now there's an expectation that the fraudulent credit card transaction is detected almost instantaneously. One of the characteristics that these the stream processing applications have is basically surrounds grouping and ordering of data. So in order to be able to process, as I said, in order to be able to process to study the evolution of different data points over time, it is important that a processing unit has the entire history, for example, for a specific time window. And that brings to it two other demands, for example, partitioning, ensuring that related data is processed together, and windowing, that we have the ability of grouping temple data together. And so this basically, for this type of problem, usually the response has been in terms of scaling and continuous scaling. Scaling storage, scaling up computing power, scaling up memory. And here's basically where in these types of scenarios, scaling doesn't necessarily mean more powerful machines. It means distributed systems. And distributed systems with very large number of nodes in terms of thousands, with or tens of thousands, with demands for with different demands for different types of resources. Some nodes require more memory, some nodes require more CPU. So in that context, it's not feasible to just manage to do a do-it-yourself approach with managing these nodes, which is why the target platforms for these types of applications become to be more natural, platforms that have resource management capabilities, whether we talk about public and private cloud, we talk about cluster managers, like YARN, for example, or Kubernetes or Mesos, or we talk about full application platforms like Cloud Foundry. So that's basically the meaning of the term cloud as a target for large-scale distributed applications. And in terms of architecture, it turns out that the microservice pattern actually fits this model very well. It brings with itself the typical benefits of microservices, like the scalability, isolation, obviously agility, the bounded context model, and but on top of all that, for data processing, for example, microservices bring something a little bit more, which is, for example, tuning process-specific resources. As I've mentioned previously, different types of applications have different types of requirements, and being able to manage them on a platform becomes critical. On a processing node, will require more CPU, but the data enrichment node that actually keeps a large memory cache requires more memory. So you need to be able to manage this kind of thing easily. And what's specific for these microservices is event-driven interaction, both as a function of really what they process is the continuous flow of events. But event-driven interaction actually brings a lot of benefits beyond for microservices in terms of communication decoupling, distributed data consistency, for example, you can avoid like communicating like through messages, for example, and avoids, for example, the issues that you require distributed transactions, or you trade off the ability of actually running and like running a transaction across an entire group of microservices for the eventual consistency of them processing events as they happen at their own pace. And this is basically, I'd like to start by digging directly to Spring Cloud data flow and running a quick demo, which is an application that receives data from HTTP and writes it to a file. And the application actually consists of two microservices. One is the HTTP receiver, one is the file writer that communicate through a pipeline. And you see the stream definition here. So if I go to, already have Spring Cloud data flow started. If I go to the console, I can actually go and create the stream, right? I can create demo, and then call it definition, HTTP. Right, and I'm going to go and deploy this. Right, and then once I did this, I can post data, so I can actually monitor the file. Let me just post some data first. I made a mistake. I forgot to post the data. So I posted the data, and if I go and look at the file, I was trying to, it's here. I can post more data. And I can see the data being appended to the file. So basically what I had here was, let me just show you very quickly, I had two applications running, an application called HTTP source and an application called file sync, communicating with each other over a shared messaging system. right? And this is basically kind of the, in a way, the end goal of developing and deploying microservices, to be able to describe these data pipelines using a very succinct syntax, like the one that you see here, right? With the extra parameters for the port and location. And in what follows next, we're actually going to go and deconstruct this and take a look at the components that actually make this possible. And I'd like to start first with Spring Cloud Stream, which is the actual component model for these pipelines. Both the HTTP application and the file application, actually, that you saw, as you've seen, they are actually running jars, and they are both built with Spring Cloud Stream. Spring Cloud Stream is a framework for developing message microservices. It is built on top of Spring Boot and Spring Integration. Spring Boot provides the ability of running full stack standalone applications, operational control, configuration, and basically jar support. Whereas Spring Integration provides the entire messaging infrastructure, connectivity to external messaging system, as well to any other kinds of middleware, so JDBC, Cassandra, Mongo, anything you can imagine. Of course, simplifying the work of writing these applications is not only a matter of putting together different components. It's actually, Spring Cloud Stream takes it a little step further and provides its own opinionated primitives and abstractions that encapsulate the patterns that I think are most useful for working with message-driven microservices. And we're going to go over these patterns in detail in a bit. The other component is, like, for simplifying the actual connection to the messaging middleware, it provides a pluggable middleware binding API, which, again, on one hand, it's essentially reusing the already existing components of Spring Integration, but at the same time, it isolates the user from the nature of the middleware. So the middleware binding API combined with the opinionated primitives actually allow you to reason at a completely abstract level. And we'll see immediately when we write the demo how that actually plays out. In a nutshell, a Spring Cloud Stream application consists of Spring Integration-based application core that communicates with the external world through input and output channels. The application declares these channels, and it's the job of the framework to instantiate them and to connect them to the middleware. The connection to the middleware is done through an abstraction of its own called the binder. And you have different binder implementations here for Kafka, for Reddit, for Rabbit, for Gemfire, for Redis. And one of the jobs of the binders in combination with the framework is to enforce these opinionated primitives and patterns onto the way the application connects. So you get that out of the box, you get consistent behavior across different middlewares, as we'll see in a minute. In a 10,000 feet nutshell, you can see all these input and output channels as ports, right? You can use whatever encapsulation analogy you want. Circuitry, for example, right? You can think of electric circuits basically connecting to like providing sockets, and then communication channels really connecting these sockets together. So here it's important to kind of stepping a little bit further in this diagram. The communication model of Spring Cloud Stream is publish, subscribe, right? So here you see, for example, the different applications basically talking to shared topics. And they're not talking only to each other, they can talk to any kind of other applications, whether they're not necessarily Spring Cloud Stream or may not even Spring boot, for instance. They may not be even Java, because if the messaging middleware actually has connectors for those other languages. It's a very powerful paradigm for interoperability, right? And the publish-subscribe semantics, which is probably one of the first opinionated choices that String Cloud Stream has made, is based on the idea that, generally speaking, these types of applications, in these types of applications, especially when it's better to for the different microservices and different components to be decoupled from each other. So, for example, if the same data is processed by two different services, there is a benefit of the sender not knowing actually who the list of final recipients. So, essentially, each service is encapsulated and receives data and sends data, and who else is the recipient of that data, they don't care. And a good example for this is we actually have, like, on one of the links that I will publish at the end, there is, for example, an Java processor that does for processing sensor data, which receives data from an HTTP endpoint. That data is sent to a topic, to a topic called raw sensor data, and then there is processed in two steps by an average processor and another processor that calculates the hottest end sensors. And the benefit of the publish-subscribe semantic in this case is that it's very easy to insert new microservices into this architecture. For example, we might want the data to be ingested into HDFS. We just add another application as a recipient of the data from raw sensor data. Or we want to do some fault detection on the averages, right? The fault detection process just monitors the averages over a given period of time. So a fault detection component can just become a recipient for the average data without disturbing the existing application flow. And that comes all natural because this is actually baked into the framework. On the other end, it's not only about processing, let's say, dumb data as it arrives. It could be the same patterns, for example, applies to a more, let's say, more traditional application integration solution. For example, orders, like if you have a pipeline where orders are processed and sent to billing and then sent to shipping, you can insert new components that react to the orders, for example, by issuing rewards, or you can audit the billing, for example, and based on the data that has flown through the orders and build topics. So I think one of the essential aspects here is that this basically kind of covers both the data streaming and event-driven use cases, and it makes it very easily to create microservices that interact with each other and stay decoupled. Of course, one of the challenges with making everything publish-subscribe is that we want to scale, and when we want to scale, we wouldn't want, like, while we want separate applications to receive the same data, at the same time, if you want to scale, we don't want the multiple instances of the same applications to be recipients of the same data, right? It would be very, very painful to ensure that an order is not processed twice. So Spring Cloud Stream enforces the concept of consumer groups, which is borrowed from Kafka, but it's applied consistently to all binders. It's an example of how it applies abstractions to its binder, to different binder implementations, and basically aligns integration with the different types of middleware. And also the concept of durable subscriptions. So multiple applications can participate in a group, and if they participate in a group, then only one member of the group will receive one message that is broadcast across groups at any given time. And also, groups are, like by default, group subscriptions are durable, which means that even if no application in the group is available, once they resume and come back, they will receive the data that they have lost. So that is kind of guaranteeing that there is some flexibility in creating these topologies without any data loss. Another important feature that's built into the framework is partitioning. So partitioning is especially a requirement for stateful processing scenarios. You can specify, like for each of the, for every output of a Spring Cloud Stream application, you can specify a partitioning logic, which essentially will ensure that data is grouped together according to that logic. And conversely, inputs, on the other hand, can be bound to specific partitions. What does that give you? It gives you, it ensures that, for example, if you have an average calculator, you're calculating the average for all the values of a given sensor, right? You don't scatter values across different components and end up having multiple and inconsistent values. Again, this is an important concept of stream processing, and it's implemented out of the box by Spring Cloud Stream. In terms of programming model, as I said, I don't want to spend too much time here because we're going to build this, but for reference, it's based on, so when you write an application, you basically declare its ports, its inputs and outputs through an interface that is added through this enable binding annotation. And then these channels can be either used as inputs and outputs channels for Spring integration components. So Spring integration is a first-class citizen in this scenario, or Spring Cloud Stream provides an annotation of its own, Stream Listener, which is analogous to the other listener annotations in the Spring messaging world, Rabbit Listener, Kafka Listener, JMS Listener, message mapping for WebSockets, which in addition to mapping messages and creating a connection between the method, the annotated method and the input channel, they actually perform type translation and coercion according to like if the incoming message has type information. So for example, a message that contains a string, which is a JSON, like a JSON string and has a content type of application JSON added as a header in the message, will be translated directly to a POJO specified as argument. And again, this allows you to do type safe programming without necessarily having to share your classes, right? This is a summary of pretty much like what I said, like the different strategies, the different options that you have for binding. So Spring Cloud Stream essentially provides a number of out-of-the-box interfaces, defining channels like source or sink or processor for the case where you have at most one input and one output channel. But you can also define your own interface with as many inputs and outputs as you want. And Spring Cloud Stream will ensure that they're bound. Or another example of an extension is the processor extension for Rx jobs. We have examples that actually show you how to write Rx Java, how to write functional transformations of streams of messages. The binder SPI is very simple. It consists of two methods, bind consumer and bind producer, and basically they encapsulate all the information the broker needs to connect destination on the target middleware to the channel supplied as argument. Whether it's like producer, for example, output channels are bound through a bind producer call, and input channels are bound through a bind consumer call. And we can also specify, as I said, as arguments, destinations and groups. And the interesting thing here, I guess, kind of lifting the hood a little bit and getting into a bit of detail, is that these calls actually translate into the native middleware support. So for example, for Kafka, binding a channel to a topic actually bounds to a Kafka topic, right? For Rabbit, producers are bound, for example, to a topic exchange, and the different consumer groups are bound to queues bound to that topic exchange. Again, the point that I'm trying to make here is that common patterns and common primitives are actually transparently mapped into native middleware support by the frame. So in order to understand this a little bit better, let's start writing a couple of microservices and see how that plays out, right? So what I want to do right now is to write a bunch of Kafka, a bunch of microservices communicating through Kafka. So first, I'm going to clear my Kafka instance. All right, I'm just going to start with a clean Kafka instance, and I want to also show you how Spring Cloud Stream creates topics and manages them. So let's create, for example, a very simple application that sends messages. We'll call it a greeter. So the greeter actually is part of the group. Let's say WebInar, call it a greeter, right? And we're going to create this example through the Spring Starter of STS, but you can also create it using Start Spring.io. So Spring Cloud Stream, for example, what does it mean is that Spring Cloud Stream has its own starters, right, that allow you to basically just get started with creating your messaging application. And I'm going to create this greeter using, it's just like a web interface, but actually baked into the IDE. I'm going to choose the snapshot version so that I can get, let's see, more up-to-date changes. I'm going to add stream Kafka as a dependency, and I'm going to finish. And by the time the initializer has finished creating this project, what it did essentially was to create a Maven project with a POM that has a dependency of Spring Cloud Starter Stream Kafka. And Spring Cloud Starter Stream Kafka basically pulls in Spring Cloud Stream and the Kafka binding. So all I have to do is just go on and create the example. I'm going to create a source, so I'm going to add enable binding. I call it the source. Okay. Takes a little bit to do the completion. Okay, and let's found the source class. Okay, so we're going to create, now we're going to create an application that, so I'm going to say hello. This is our nice, and return a hello and the timestamp. Right, and in order for this to be actually integrated with the source channel to actually send, I'm going to add Spring integration annotation, which is inbound channel adapter. Okay. And I'm going to specify that the channel to which this channel is bound is source.output. So basically, the output channel of this greeter application has been bound to this channel adapter that pulls by default this method every second, returns a message that says hello, system current time mil is, and is gonna write it and publish it to the output channel. And by binding that output channel, actually, I will guarantee that it makes its way to the messaging system. So the next thing that I want to do is to decide what destination, what topic do I want to write to. So obviously, by default, it's going to be output, but that's kind of confusing. So I'm going to add destination. I'm going to say that I want this to be written to a copy called messages. And I'm going to start the application. Let me just do something here. Since I'm going to start multiple applications, I want to make sure that their ports don't clash. So now, this has created the application. As you can see, a topic called messages has been created in Kafka, right? And the application has started publishing messages to it. Obviously, we can't see any of these messages, so why don't we create an application that actually listens to them? We're going to call this application log receiver, because it's a receiver and logs. And it's a stream Kafka application as well. And so this application actually is going to receive messages. So I can put, for example, in a string, I'm going to log the message, right? And at the same time, so I'm going to just write the message. It's very simple, right? And in order to connect this application, in order to connect this logging method, first I'm going to create a bound interface, which is going to be sync in this case, which means that this is an application that receives messages, And I'm going to say that I'm going to create a service activator to actually connect this application, to declare this method as a service activator bound to the input channel sync.input. Okay. Now, that is not enough yet. So by default, if I launch this, it will connect to the default name of the channel, which is input. That's not what I want. I'm writing on messages, right? So what I'm going to do next is go here and adjust this as a string plus stream findings. I'm going to call it input. I'm going to call it destination. I'm going to call it equals message. Okay, I'm going to do this, right? And I'm going to do the same server port equals 0, so that the Tomcat instance that starts with the application actually listens to a random port. And you see the log receiver has started and it receives messages, and the message is sent by the other application. So just very easily, we've created two applications that talk to each other through messages. They talk to each other over Kafka. That's pretty cool, but what if I wanted something a little bit more structured? I mean, obviously sending strings over is nice, but it's not a very easy way to structure a message, right? So I can send, instead of sending plain strings, I could send JSON. So what I'm going to do is I'm going to create a new object that's going to be translated to JSON, and I'm going to call it a greeting. So I want things to be structured. I'm going to create, I'm going to call it greeting, right? And create a getter in the setters. And I'm going to make the greeter application to actually, instead of returning this message, to return a greeting. And not only that it returns a greeting, but actually the greeting is populated with the old message, right? So this is it, right? I can start it. Now, what I want is for this application to send data as JSON. So I want the greeting object to be translated to JSON. So what I'm going to do is I'm going to tell the output channel that it should output data as application JSON. So now the greeter starts. I'm going to start the receiver as well. And I should see, I should see the greetings actually coming in as JSON messages, right? And now let's say that I want to process this data as a POJO itself. So I will add a new processor that can receive this JSON and transform it. So I'm going to call it the greeting handler. And going to be Kafka based again. And this greeting handler application can actually, so this is going to be a processor, right? Okay, I'm going to call this a processor. The processor interface, okay. And what I'm going to say is I want to decode this incoming JSON into an object, but I don't want to use the original class, right? I don't want to share classes between my applications. So I will create a new POJO to store the data. So this is going to be like this, right? And I'm going to create a stream listener on processor input that sends data. the output, right? And I'm gonna do two things. I'm going to extract the payload and send it further. Right? But then I'm going to dump just to see that it's an instance. Just dump the instance. Yeah. Okay. So now this comes in handy here. So this application now is gonna receive data instead of, it's gonna receive data from messages, right? And it's gonna output them to transformed. Why don't we start it, right? Whereas the log receiver will get information from transformed. And you see, basically, you see the the greeting handler application dumping received greeting instances, shows that the transformation has been done correctly. Whereas the log receiver is dumping the extracted message that the greeting handler has produced for them, right? So what we just did was to create a bunch of microservices that talk to each other, that can exchange messages, that they connect easily, but also can transport, for example, can do transformations from POJOs to portable data formats such as JSON and so on. It actually can communicate that information to each other. So this is basically a very, very simple example of how these Spring Cloud Stream-based services can interact. Now, at the other end, obviously, there are a ton of properties that you can configure on a Spring Cloud Stream Services service. Apart from the destination, you can surely do things like stream, for example. You can configure the, you can, for example, configure some, okay, completion has, I can do something like this. Expression for partitioning and something like that, right? And it's actually pretty, well, it's easy to do this while you're writing these applications. It's actually quite a task to actually do this for each and every application that you put together. So this is one of the jobs of this is where basically Spring Cloud data flow kicks in as a portable orchestration layer for streams and tasks. And we're less interested about tasks right now. We're going to focus on streams. But the idea is that if you remember the example that we run just in the beginning with the HTTP pipe file, well, that is basically an example where Spring Cloud data flow orchestrates two independent microservices written using Spring Cloud Streams. So it basically launches them, it configures them, input destination and output destination so that they can talk to each other, and it configures other parameters, like, for example, partitioning, and so on. Apart from that, Spring Cloud data flow provides, has a RESTful API for interacting. So not only you have the shell, but you actually have an API that so you can do the same job of launching tasks. It has its own UI. And it has a number of out-of-the-box applications for common use cases. So if you go to, if you will go to Spring Cloud Stream modules, for example, there is a whole bunch of these Spring Cloud Stream applications which have like very simple structure, like the one that we just saw, that are actually pre-registered with the application itself. So, for example, when I go and say HTTP, this is what I'm basically looking at, right? It's essentially a controller application that's a Spring MVC application that has a source channel bound, and for each incoming message, it sends it to the source, right? This is how it gets to the messaging system, and the file application is the thing in exactly the same way. Apart from the orchestration layer and translating the DSL, Spring Cloud Data Flow performs another very important job, which is it maintains consistency across, it maintains consistency in the way these applications, these streams, for example, are deployed across different platforms. It does that through leveraging another project called Spring Cloud Deployer, which is essentially provides an SPI for deploying applications to various types of runtimes. Whether it's local, that you've seen me actually deploying to, but it actually works exactly the same way with YARN, works exactly the same way with Cloud Foundry, works exactly the same way with Kubernetes or Mesos or Marathon. So essentially, from my perspective, when I'm running a stream, I don't care how it runs. It's data flow and its integration with Spring Cloud Deployer that ensures consistency across the board. And this is basically what it comes down to, right? You declare the stream, you run it, you get the applications running. What you end up with is with a number of boot applications running inside the platform and deployed through the different pluggable SPI implementations. The benefit, obviously, is that this leverages the platform's capabilities for resilience, for failover, right? In Cloud Foundry, if one of your stream component dies, it's just brought up again, right? Because it leverages the ability of scaling, right? If you request, for example, if you know that you want to deploy 5 instances of it, you just have to request 5 instances, and it is the platform's job to provision you with 5 instances. So this type of consistency, like combining essentially the translation done for the DSL with ensuring the consistency through the deployment process, is the main job of data flow, right? In terms of developer experience, so as I mentioned earlier, Spring Cloud Data Flow comes in with a number of predefined modules that you can just, which are essentially Spring Boot applications. They are pre-registered with a runtime. So when I do something like I did before, right? This let's say where it was. When I do this HTTP pipe, file, it's basically saying I want to deploy the module that has these and these coordinates, and it's actually a Spring Cloud Stream application that has the structure, and it actually lives within it. In fact, the product of building this application with a specific binder. Now, if I wanted, for example, to create my own modules and deploy them, that's very simple. I can destroy, right? And I can create, for example, a new module exactly like it's a Spring Cloud Stream application, so we can use the starter. Right, and it's going to call it uppercase. I'm going to call it uppercase, and it's going to be here. And in this particular case, I'm going to use Redis because this is what the pre-built modules use right now. And all I need to do here is essentially to create a processor. So I'm going to do the enable binding. I'm going to call it for processor. Okay, and this is essentially a transformer with input channel inbound. Sorry. Unfortunately, so once I have this processor created, I can go to WebInar, and I can do a clean install. Right, and this has installed the artifact in the Maven repository. And then I'm going to register, so I can register the module. I can specify the coordinates, the name, and the type. Okay, apparently I already have it registered, so I don't need to anyway. And then I can create a stream that actually is like the original stream, but actually passes data through the uppercase process. So when I'm sending data to the HTTP endpoint, it's actually handled by the uppercase transformer. And as you see, it lands in the file as converted to uppercase. So as you see, basically creating and registering and launching a stream using a custom processor is fairly easy. And I think that is pretty much it, what I wanted to show you. Obviously, Spring Cloud Stream supports more advanced features like taps, for example, which is a function of the publish subscribe natural relationship between stream components. What can I say in terms of timeline? We just released Spring Cloud Stream 1.0.0 RC1 today, and we're looking at releasing Spring Cloud Stream 1.0.0 GA by the end of the month. Stream Cloud Data Flow will be released in the second quarter. So looking forward to bringing this all to a final release. So this is pretty much all for me right now. What I was hoping is to show you how easy it is to build these microservices, to connect them together, to handle messages with different types of payloads and content types, and how easy it is to integrate them with Spring Cloud Data Flow and launch them as structured pipelines. So thank you very much. And if there are any questions, I'm ready.
There are a ton of questions, as a matter of fact.
Fantastic.
Do me a favor and let's try to keep the answers as brief as you can, or else we won't make it through all of them because there's like 7 or 8 questions stacked up. A few of them I've already answered, but so I'm just going to jump right into some of the unanswered ones. Ben Zhang asks, where do I specify the Kafka IP and port for the application to connect?
Sure. That's an option of the binder. So if you go here, you have a so it's a property called Spring Cloud. Okay, right now completion is a bit host, but it's something like this: Stream Cloud Stream Kafka binder brokers equals or broker addresses. I don't remember exactly. Anyway, you do it like this, right? And then IP port, something like that. There is a property that you can specify in application properties. And remember that these are boot properties, so they also support, you can configure them at runtime as well, not necessarily bake them into the application. A complete reference of our properties is here. And
all right. Next question comes from Anantha Rao. Can you specify the message time to live?
The message time to live on in Rabbit? No. Like Kafka does. Well, Kafka has its own configuration for retention, so we don't specify that as an option. You can administratively change it on the broker, and the same is true for Rabbit. So it's not part of the topic setup, but you can edit it on the administratively in the broker.
Got it. Okay. Got it. Okay. So that's sort of the implementation. That's sort of transport layer specific. So if I was to choose Redis for Rabbit,
yes. At the moment, yes. I mean, we're always open to add new general purpose features if they make sense. It makes sense to be implemented, let's say, as a general purpose feature and translate them down to the middleware. But in this case, it's middleware specific.
Got it. Okay. Next question. Is there an example of multiple outbound channels from a single microservice?
We don't have one, but it's possible. So probably that would be a good suggestion to add to our samples. No, we don't have a specific example for that. But yeah, we'll endeavor to build one. It's in the best place to look for something like that is in the tests. But I guess it would be much nicer to have an example that showcases that as a running application.
Okay, very good. Sorry, I was just typing up an answer to Anantha Rao's question so you can see it in the console, and just encouraging him to open a Jira ticket if he feels that would be helpful.
I mean,
next.
Sorry, just
sorry. Go ahead.
Yeah. Just sorry to interrupt you, Peter. I just put an example from the documentation of how an interface like that could look like, but it's not part of running an application that you can run right now.
Understood.
Sorry, go ahead.
No, not at all. Not at all. And there's some great questions online here, folks. So, make sure that, if you think if you think this would be useful things, by all means, please open a Jira ticket so that we can, or Marius, do you use GitHub issues or Jira ticket?
I would, depends. I'd much prefer to use Stack Overflow for this. Like if there are questions, Stack Overflow is the best place. If there are feature requests, then GitHub issues.
Okay, it was feature requests that I was asking about. Okay, yeah, so GitHub issues.
GitHub
okay,
issues.
Right, very good. Very good, okay. Next question from the same gentleman. So how does how Cloud Stream partitioning and Kafka partitioning relates? Do they need to match exactly?
Yes, they match exactly in the sense that any partition producer is, so Kafka partition producers write the exact partition across all the partitions of the target Kafka topics, right? So when we say this is the partitioning logic, like a spell expression or something like that, we partition by the target partitions of the Kafka topic. On the receiving end, we have rules that basically allocate partitions to instances, right? So we make sure that each instance receives a subset of the partition set of the topics.
All right, great. Last question from the same gentleman. Let's see. So for a partition, do I always need to have a partition key?
For partitioning, yes. I mean, you have different ways of specifying. You can have a spell expression that is essentially evaluated against the unbound message. So the key can be synthetic. Like if you don't necessarily have to have a field that's a key. You can just evaluate an expression, and depending on the evaluation result, it will go to one partition or another. You can also have the option of specifying a class, which implements an interface where you can put something more sophisticated. Like, I don't know, you want to do dynamic partitioning or change the partitioning logic at some point, like while it runs or something like that. That would be the place to do it. It's a property called the partition key extractor class. That's right.
Excellent. All righty. I'm not sure about this question. Question about does Spring Cloud Stream support the SAGAS pattern? SAGAS? That doesn't sound familiar to me. Does that ring a bell for you? You know what he's talking about?
I
think it might be a typo.
Right now.
Yeah, I think it might be a typo. Ram Natarajan, if you're still on the line, could you maybe clarify that question, and maybe we'll still be able to get to it?
Yeah, sure.
Let's see. Again, same question. Another question from the same gentleman that was asking the partition questions. What happens if I don't specify the partition? How do I scale the producer and consumer then?
Well, okay. Sure. I mean, you can have, you don't necessarily have to, I'm assuming that this is in the context of Kafka. You don't necessarily have to have a partition key to write to multiple partitions. If you don't specify a partitioning key, then we just use the default Kafka strategy, which is round robin. So basically, the producers will just fan out messages across the different partitions. The consumers themselves will still receive a subset of partitions. So when you say you scale up, so obviously producers, you can have as many as you want on the same topic. With consumers, again, you can have as many as you want as long as they're at least at most equal to the number of partitions of your topic, right? So you can, one strategy, for example, is over partitioning. So you can have, I don't know, 10, 20 Kafka partitions, and then you can scale up and down your consumers as much as you want. Producers are not constrained by the number of target partitions.
Excellent. Oh, our good friend David Turansky asks, what's the difference between the @StreamListener and @Transformer annotation?
The main difference is that stream listener is basically using the Spring messaging infrastructure for type conversion. So that's basically @Transformer, for example, does conversions based on does a conversion based on the conversion service, whereas we use the same message converter system that's used for the input and output channels for stream listener, except that we actually bring it closer to the method itself.
Excellent. Okay, we're almost to the end of the question list. We're doing great here. This is fantastic. This is an interesting question, which I think I know the answer to, but I'm curious to hear what you say. Ram Natarajan asks, can data flow, or I think you mean Spring Cloud Stream and maybe data flow in general, but can you do transaction management across microservices? I suspect I know what your answer is going to be.
Yeah, I think the nuanced answer is, I mean, obviously we don't support distributed transactions as such, but I think the message-driven interaction is kind of a very good substitute for distributed transactions for maintaining data consistency across a fleet of microservices, right? So ensuring that transactions are actually each write, for example, each message sent is transactional in and by itself. Each component itself is transactional. As long as it safely sends the messages and it publishes its updates somewhere else, then the other services can receive those updates and update themselves and continue and go on. There is no loss, even if the consistency is eventual, not necessarily synchronous.
Got it. Okay. Right. So not like an XA, multiple, not like XA style, where you're doing multiple, transactions across different back-end implementations. But from point-to-point messaging, yes, there's guarantees, but and transactions, but not in like the sort of XA global transaction sense, right?
Yeah, exactly. I mean,
okay.
If you had let me put it like this, in a very extreme case, if you could enroll multiple JMS consumers in an XA transaction and do stuff like that, but I think it detracts a little bit from the benefits of the architecture. So that's my opinion.
Yeah, it is a bit of an anti-pattern there. Okay, so last question. Wow, I can't believe it. We made it to the last question. All right. Bala asks, can we write a custom binder if we have existing middleware like IBM MQ series?
Oh, sure. Like if you're, not only you can, but if you want to contribute it, that would be fantastic.
Exactly. All right. Well, I think with that, we believe it or not, we made it to the end of the question list. All right, this is awesome. Thank you, everyone, so much for the engagement. It's great for us to get your feedback in the form of the questions. So really appreciate that. This is being recorded. This webinar is being recorded. So we will share the replay with you within about 2 weeks. We'll have that posted to the Spring blog and the YouTube channel so that you can get a hold of the replays and share them with your colleagues, and maybe even, catch something that you missed. I will put the URLs right now in a question into the chat window. And then we also will publish the slides at that time. So, the blog entry that contains the YouTube video embedded will also have a slide link. If you happen to just subscribe to YouTube, we'll get it there as well. You get the slide link there as well. So if you want a kind of a faster notice, would recommend that you just subscribe to that Atom feed at spring.io blog. And you not only will get a very, as soon as it's available notice about the replay, but you'll also get all the other killer blog content from the Spring team. So highly recommend that you consider doing that. I'm just going to post those replay links to the question Q&A panel right now, so you have them handy. Bear with me for a moment. Excellent. Okay. All right. That should be showing up now. So that'll be available within 2 weeks. And then if you're looking to get a hold of software, if you're looking to get a hold of bits, you can, really we strongly try to encourage you to use Maven and Gradle as the preferred way to download software. So if you are on a closed network or desperate for an HTTP download for some reason, you're on a closed network or a military network or something like that, or, behind 200 layers of proxy server, you can get HTTP downloads if you absolutely need them from our Artifactory instance, and that is located at repo.spring.io. And that's repo.spring.io. But really, if at all possible, we encourage you to use Maven or Gradle. It's just a vastly superior experience. And then, come back and join us. We are going to be hosting another webinar on the Ratpack web framework a little bit later this month. And I'm just putting the details again in the Q&A panel right now. Hold on a second. It looks like that didn't quite work. Let's see. Hold on. There we go. So the URL for the next webinar is on March 31st is up there. And if you're interested in the Ratpack web framework and how that relates to Spring Boot, please come join us on Thursday, March 31st. Okay, and I think with that we're pretty much all set. Marius, thank you so much for talking us through this milestone release, and it sounds like we're going to be having a 1.0 GA. Did I hear you correctly at the end of the month?
Yes, even sooner. Like it's the last stretch. So yeah.
Awesome. That's fantastic. All right. Well, again, thank you so much, Marius. Any comments you want to make before we close it up?
Just want to thank everyone for attending, you for organizing, and have a great day.
All right. Take care, everyone. See you hopefully in the next webinar. Come back and join us on March 31st for the Ratpack. Have a great day.